So now we've looked at the urea cycle, I want to clear a bit of confusion that can happen with this molecule, NH4+. So this molecule is ammonium, and though you might see it written as NH3 in that first step of the urea cycle, I would always write it as ammonium because ammonium is the ion and it can be found on its own, while ammonia is NH3 and is found inside chemicals. So that's what I would remember there, and I hope that clears up the confusion about that. And the body removes ammonia from chemicals to form ammonium, which is removed by the urea cycle. So that's really important to remember. So now let's go back and have a look at some other things in the urea cycle and look at where they come from. So in the first step of the urea cycle, we have this NH4 molecule and this ion, ammonium, as I just described. But where does it come from? So it can come from a variety of places. First up, we have the deamination of glutamate to alpha-ketoglutarate. So glutamate can be deaminated to alpha-ketoglutarate. So we're removing an amino group from the molecule. So we remove this NH4, which is the ammonium, which can then go into the urea cycle. So this is happening inside the liver. And an NADP is converted to an NADPH in this process, and the enzyme is glutamate dehydrogenase. Okay, so that's the first way that the NH4 can come from. So that's the first example. Then also many other different amino acids can be turned into ammonium. So it's not just the glutamate to the alpha-ketoglutarate. We could also have at the same time another amino acid. There's so many that you can look up and have a look at. There's a lot that can be in the body. So amino acids are then converted to alpha-keto acids. So alpha-keto acids contain a carboxylic acid group, as shown here, and a ketone group. And you probably don't need to know the chemical structures too much in detail, but just know that through an aminotransferase reaction, other amino acids and alpha-keto acids can react with this alpha-ketoglutarate and glutamate with the removal of an NH4. So, but primarily, as you can see, I've asterisks in light blue. The NH4 plus is coming from the deamination or an aminotransferase reaction, and we're removing this ammonium from these amino acids, primarily glutamate, which is asterisked in light blue, which then gets converted to alpha-ketoglutarate, like so, or vice versa. As you can see, the reaction is reversible. So that's two examples. The third example of where NH4 comes from is glutamine. So glutamine is another major transporter of nitrogen to the liver. So I'm not exactly sure why glutamate can't travel directly to the liver by itself, and neither were my lecturers or my tutor. So I would just go with the fact that glutamate, for whatever reason, can't be transported by itself from muscle or peripheral tissues directly to the liver. So we have to convert it to something else so it can be converted to the liver. Just go with that in this case. So here we have an alpha-ketoglutarate, which becomes a glutamate in the muscle or peripheral tissues. And this is a deamination, so then we lose this NH4 group. And the enzyme here is glutamate dehydrogenase. Then this glutamate becomes glutamine through glutamine synthetase. Synthetase, we've got a ATP going on here, and ATP is used, and this ammonium is removed, and these can go into the urea cycle when they're transported to the liver. The glutamine can then be transported through blood vessels or however it gets through the body to the liver, and then we can convert it back to glutamate through glutaminase, which is the enzyme here, and then the NH4, which is the ammonium, gets moved off, and then the glutamate goes back to alpha-ketoglutarate. Remember that this process was reversible, and NADP gets converted to an NADPH, and it's the enzyme glutamate dehydrogenase here. So these two ammonium ions can then enter the urea cycle. So that's how we get glutamate to glutamine, so that we can then transport it to the liver where it can be deaminated, and then we can get that ammonium to go on the urea cycle. Now this is used when they're starving off, when your body's starving or when you're fasting. And that's because it requires energy. So it's when you're desperate and you want to break down this ammonium really quickly. So that's when we use this process. So either, just to recap, so the NH4 will either come from a deamination of glutamate to alpha-ketoglutarate directly in the liver. Also, the NH4 can come from many other different amino acids through aminotransferase reactions. And also we can get this NH4 coming in from peripheral tissues. And we remember that glutamate can't really travel by itself. That's what we're going to conclude, and that's how we're going to think about it. So we've got to convert it to glutamine, and so that it can go into the body. So just remember that key concept that glutamate is not going to travel by itself to the liver. It needs to be converted to something else first before it can be transported to the liver. So just on that note of glutamate needing to be transferred to something else. So where does the glutamate come from? So it comes from transamination reactions. So like I said before, the glutamine can be converted to glutamate in the liver, and we can convert glutamate to glutamine so it can be transported to the liver. Alternatively, we can get the glutamate from alanine, and this is called the glucose-alanine cycle, and we undergo a transamination reaction as well. So if glutamate is in the muscle, it needs to be converted to alanine so it can be transported to the liver. This is the primary way that it happens. As I said, you use glutamine in starvation. So the glutamate comes from alanine or alanine, whatever you want to call it. So, and this is the glucose-alanine cycle. It's not a huge, big cycle. It's just a process that you should just remember. So remember that we've got this alanine, and so it's a transamination reaction. So we'll start up here with the glucose. So glucose can be broken down to pyruvate through glycolysis. And then this pyruvate can undergo transamination reaction with an alpha amino acid and an alpha keto acid, as shown here. So the example here is glutamate and alpha ketoglutarate. And basically we transfer, so we've got an oxygen being moved to pyruvate from alpha ketoglutarate, and then NH3, and it's an NH3 here because it is ammonia, which is found inside chemicals. So the NH3 then gets transported to glutamate. So they kind of do a little swapsies. So a swap and a swap. So that's how I like to think about it. So we've got this transamination. It's a bit confusing. You just got to write it a few times until it sticks. And then you've got this alanine. So we've got two alanine because two pyruvates are produced from glucose, as we know. So this alanine can now be transported to the liver. And then the alanine can be transaminated again here in another process, and the glutamate can then be deaminated, and we can get that NH4, which then goes into the urea cycle, and then it can transport back. So we use the alanine to do a similar transamination reaction here, which goes into the urea cycle, but then it's a process where the alanine gets converted back to pyruvate, so it goes backwards, back to glucose, and it's just this constant cycle. It's a bit to wrap your head around, but maybe if you just pause this video here and just have a little bit of a think about that concept of how we're transporting things around. So remember, the glutamate can't go by itself. We've got to transport it by converting it to alanine first, and then we're going to move the alanine to the liver, and then the alanine through some reactions here. So through some deamination and transamination reactions as shown here. That's what's happening here. We can get a glutamate, then glutamate can be deaminated, as we can see in this reaction here. So we can remove the NH4 molecule by converting it to alpha ketoglutarate, and then the NH4 will enter the urea cycle. Just pause the video here if that's a bit confusing and have a bit more of a think about it. So I've also written, where does the aspartate come from? So as we know, there's an aspartate that enters here from citrulline to arginosuccinate. So this aspartate can also come from a transamination reaction. So as you can see here, the aspartate exchanges the NH3 with glutamate. So remember, NH3 is ammonia, the molecule found inside chemicals, and then the alpha-ketoglutarate glutarate goes to oxaloacetate and the oxygens transfer. So that's where the aspartate is coming from. It can also be transported out of the malate aspartate shuttle, so you can go look at the video about that in a little bit more detail. But yeah, it's mainly the transamination reaction when we're talking about the urea cycle. And as you can see, the enzymes for this reaction, so the first one that we saw, which was with the glucose-alanine cycle, with the alanine being converted back to glutamate, the enzyme here is alanine transaminase, and with the aspartate mainly going to enter the urea cycle through the transamination reaction, the enzyme here is aspartate transaminase. And here we've got B6 written here, so I've got an asterisk here to follow that. So pyroxidyl phosphate derived from vitamin B6 is a cofactor for this reaction. So vitamins are chemical precursors and they can be used as cofactors in reactions as shown here. So that's the basics about transamination and the urea cycle.